Hopefully you're all seeing the opening page for the presentation. Thanks, Christian. Thanks to obviously the Biochar research group and NCHAR for allowing me to present in the presentation today. I am Alex, as Christian introduced. I work for Severn. We're an energy agency, but we have a history of working with community groups and community energy projects. And about 10 years ago from that work, we started working on kind of small scale, farm scale anaerobic digestion, and started working with biomass management in rural areas. And really about 7 years ago, stumbled down the lovely rabbit hole that is the world of biochar and biochar production and everything that it can bring. So we now work on a range of projects, myself and my team on the Sustainable Technologies team, and we work with both academics and industry, trying to, I suppose, grow the sector and also answer some of the questions around the development of pyrolysis and biochar, particularly here in the UK, but also on the European level. So the project I'm here to talk to you today is one of a few that we're operating at the moment, but this is one that we're doing in conjunction with a pyrolysis technology provider called TerrAffix, who are based in South Wales, who've been producing biochars for over 10 years now as part of their hydro seeding programme and land management programme, and also with Biochar Welsh Water, one of the large water companies in the UK, focusing on basically their post anaerobic digestion sludges that they produce, and what could be done with those with pyrolysis and the biochars they create. So a little bit of background for you and how this consortium, this group of partners came together on the project. We work on at Severn. I work on a project called 3C, which is creating circular carbon economy. It's a follow-on project to a project called Redirect, where we produced a range of active carbons, activated carbon biochars from a whole host of bioresources, including, not including sewage sludge on that occasion, but including kind of challenging and invasive species and more traditional waste wood products and biomass products. And that was to target the use of active carbons in the wastewater industry, and could we close a loop for the use of homemade biochars from waste products in local municipalities. That wasn't it was an interesting project, and it had positive outcomes in terms of the active carbons you produce, but it wasn't of much interest in the UK to the water companies because of some of the treatment processes they use. So we quickly identified that some of the biochars rather than active carbons we could produce would be worthwhile exploring, and the process itself would be of interest. So we developed the relationship with Biochar Welsh Water, and we started building our project together. So the purpose of the project was to bring together all the kind of key stakeholders that would be needed to consider pyrolysis for the treatment of post-advanced anaerobic digestion biosolids, allow the industry to witness the plant in operation, witness the way it treats the biosolids, witness the biochars it produces, consider kind of the possible future opportunities for upscaling to multiple sites, the implementation of the end-of-use product. Excuse me, my cat has joined us. And also raise any kind of concerns and industry considerations that would be really relevant for us both during the pilot, but also progressing on beyond into the next phase. We kind of a key part of working with industry is considering that the drivers for change across the water industry in the UK, not just for Biochar. Biochar Welsh Water have their own 2050 zero carbon strategy, and obviously the potential to treat some of their waste products and turn them into carbon products that can potentially be counted towards their zero carbon economy is very interesting for them as a standalone concept, let alone when you factor in the treatment of the waste itself. They also view it as a potential opportunity to kind of future-proof themselves against future regulation change. Regulation in the UK at the moment allows the spread of the biosolids to what they call the land banks, so to agricultural land. There are regulations to control that spread, and those regulations are tightening, particularly in Wales, but also across the whole of the UK. So there's an anticipation that their practices will need to change. They're also looking for, reduction in their OPEX costs in terms of the transportation of the sludges. Obviously, we can reduce the scope of the sludges by 90% by turning into biochars, and there's a lot less movement, which is a positive for them. And they're also keen to consider what the resource recovery opportunities are. Obviously, at the moment, the biosolids are spread back to the land bank, and that's for nutrient and resource recovery rationale. So they don't necessarily want to see those nutrients and resources just kind of being thrown away or sequestered into a non-useful subject. So that's a consideration when we're looking at the end product. The pilot plant was the pilot project, I should say, was developed over 3 phases. So the first phase was a research phase conducted in collaboration with Aberystwyth University and the University of Kassel in Germany. They are both partners on the 3C European project that we work on. So we took some of the sludges from one of the wastewater treatment sites operated by Cymru Welsh Water, and they were sent off for initial analysis and characterization, and then for carbonisation in a lab scale pyrolysis machine, and then the resultant biochar was then analysed and tested against EBC level classifications for biochar to give us an idea of where those biochars sat in the kind of usability scale. Phase 2 is the operation of the pilot plant itself, where we are blending a range of a larger set of the biosolids we've taken from the water companies, mixing it with a range of different feedstocks, primarily wood chip for characterization purposes, but in the long run looking for blends with other waste products. And we're doing that at a range of different percentages to find the optimum blend for our process. And then phase 3 is potential on-site operation of proof, basically the last stage where once Dua Cymru are satisfied with the way the technology works and the potential, look to run one on one of their sites to complete the final proof of concept. So the lab scale pyrolysis was done on the lab reactor that you can see in the top right corner of the presentation here. The bottom left image is well, in fact, the bottom 2 left images are the biosolids once they were dried, but prior to carbonisation. And then the bottom right image is the kind of the carbonised biochar itself. Now, the purpose of the lab scale was to replicate the pyrolysis conditions of the proposed pilot plant and provide a baseline for those phase 2 trials. So the pyrolysis was conducted at 2 temperatures, 400 and 750 degrees C, with a retention time of 30 minutes. We determined the kind of the ash contents and the main elementals, some heavy metals and bulk densities, and higher and lower heating densities. The pre-treatment of the biosolids was in a 60-degree dry oven, grinding using a 4mm sieve. So we had a kind of homogeneous feedstock for the carbonisation process. The results were pretty much as expected, I suppose, in some ways, but not as expected in other ways. What we found was the overall reduction in yield was lower than expected. We were getting a yield of about 30% during the lab stage, where we were expecting closer to 90% during the pilot phase. Sorry, a 10% yield, so 9% reduction during the pilot phase. But in terms of the calorific value, because the sludge itself, the biosolids, are post-advanced anaerobic digestion, obviously they've already been stripped of much of the calorific value. So they are coming in at around 4 megajoule calorific value, where the process generally needs about 11 to 13 to be self-sustaining. So we anticipated that it wouldn't be particularly sustainable from a self-sustaining perspective without any blending, and that was proved within the lab scale. Although it did run, but it wasn't as effective as we would have liked. But it gave us a starting process, and what was encouraging was there was still volume reduction, and the kind of the heavy metals and elementals that we did measure against CVC, obviously we didn't do a full suite, also offered encouraging results, as in terms of the reductions being within classification levels that would be acceptable for further use. So it was a good starting point. and led us on to the pilot plant itself. Now, the pilot plant itself had kind of a set of key objectives, I suppose, that we negotiated with an industry partner. So it was all about characterization of the feedstocks, how we were going to dewater them, what the drying technique would be, what the best drying rate could be achievable, and in the long term, what the heat mass balances of the plant in terms of the heat recovery and the drying requirements will be, the potential process throughput, and the potential production of energy, whether that be the heat recovery or external energy production from that heat, management of the emissions in line with our industrial directives that we have here in the UK, and kind of basics along the lines of power consumption, heat recovery, cost of units of materials, and then finally the actual biochar quality and production at the end, and of course the total life cycle of the process, because that's the key consideration from the industry perspective, is what is the life cycle benefit for them. So I'm going to play you a quick video. There's no sound on this video, but I'll talk through it. So apologies, because we have got a professional video in the making, but it wasn't ready for showing today. So this is a really quick kind of 1 and a bit minute video showing you the pilot plant itself in situ on our site in Swindon, which is the Water Research Council site. This is just a bit of a promo bit from TerrAffix itself, explaining their processes. But shortly we'll come on to the pilot plant itself. As I said, we're operating the pilot plant, and during the pilot as blending with wood chip. This is because a lot of the work that TerrAffix do at the moment is hydrosealing development work. So they have an open supply of it. So this is the pilot plant in situ. So we have 3 shipping containers, 2 20-foot and 1 40-foot. This is the feed hopper. It's up a conveyor belt drop feed system, so that the feed is just carried up and dropped into an auger at the required rate. The auger then drops it into the half. It's got a multi-deck drop half, so it consists of 5 decks, each rotating, and as the biochar works its way down through, it reaches total carbonisation before dropping out into another auger that goes into the 3rd shipping container and is produced out into as biochar, as you can see, which can then be managed. There's some better shots of the plant coming up. The plant has an external has a separate thermal oxidizer that pulls the gases off, and the retention time of the plant at the moment is set at 120 seconds. So it's very fast pyrolysis with temperature range of between 700 and 900 degrees. So the front box there is the half, and behind it is the oxidizer. And then the flue gases are pulled off and brought through our scrubbing system. So we've got a wet scrubbing tower, and then an activated carbon recovery draws, and then out of the flue. Now, when the plant is running purely on biomass, the wet scrubbing system can be bypassed because we don't need to utilise it to meet our emissions within the UK. But for dealing with biosolids and hazardous waste effectively, then we need to utilise the flue system. What the flue system and the carbon, the activated carbon filter give us the opportunity to do is to look at what's happening to certain contaminants once they're volatilized, because we know they're not ending up in the biochars, but certainly for parts of kind of certain heavy metals and also PFAS, what we're going to be looking at later on in the process is what's actually happening to them if they're not in the biochars. Are they being volatilized? Are they going out through the flue? Are they kind of being picked up in the wet scrubbing system, in the carbon filters? So we're going to be doing some work on that later, but I don't have any update for you on that right now, I'm afraid. A few questions coming in. I'll keep going and come to the end. I guess Christian's probably the easiest thing to do. This is just the process concept of the plant itself, and a kind of bit of a still shot of the plant. Like I said, it's 3 shipping containers, 2 20-foot and 1 40-foot. They're relatively mobile in the sense that all shipping containers are. The plant throughput of this one is about 200 kilograms an hour, about a cube an hour. of throughput, but the same size shipping container can hold one that can go up to about 600 to 700 kilograms an hour, and there's a second plant currently in production to show that. So the footprint remains the same despite the quite drastic increase in processing capability. Obviously, what you would need then is obviously better storage and more storage externally to the two shipping containers on the sides, which are at the moment just for the in-feed and out-feed process. The heat can be recovered from the thermal oxidizer and run back through the drying system. We don't have a drying system on site at the moment. It's part of the next stage of the development of the plant as well. In terms of the biochars that we have produced so far, we have completed a series of blends of the biochar. We have run 100% biosolids, we have run 90% biosolids, we've run then down the other end of the spectrum at 20% biosolids and 10% biosolids. Now, the 10% and 20% biosolid blends have both gone off for EBC level classification, and we know that from the resultant biochars we're producing meet at least the basic materials level of the EBC, which means that we have a potential end use for our biochars at the end. And other than some of the heavy metals, the majority of them meet the higher grade agricultural use levels. So we're working on improving that and seeing what the optimum blend is and what the outcomes of that will impact our final delivery, our final use case. Most importantly for us, one of the main considerations is our emissions and particulates, and we meet all industrial standards currently required within the UK, so that's really important. And obviously that's an EU directive that the UK still follow, so therefore we meet the EU directives as well. So in terms of analysis, what we do know in terms of our biochar, both our 10% and 20% blends, is that we have done some analysis to show the stability, because obviously we want to know that the carbon can be sequestered comfortably and securely for the required times in order to really get the full benefit of the carbon sequestration potential of those biochars. And the 10 and the 20% biochar blends both sit within this kind of this area of really strong stability that we would want to see from our biochars, to know that they're not going to degrade. So that's encouraging. And an interesting thing here with the relative enrichment factor, looking at our biochar 10 and 20, is both the 10% blend and the 20% blend follow similar trends in terms of the level of enrichment. Obviously, anything above 1, which is beyond the end of the graph here, would mean a positive enrichment. Everything below 1 is a negative enrichment relative to the yield. So we are reducing all of these heavy metals by quite considerable amounts, no more than 30%, the highest one, which is the nickel. And broadly speaking, as you would expect, the ones with the higher level of biosolids have got a slightly higher or slightly reduced enrichment factor compared to the lower biosolids. So we'll be continuing this development and continuing both this analysis with all of the blends we do, ranging all the way up to 100% biosolids to give us the best understanding of the biochars we can produce and their potential end uses. Some of our challenges we're facing is broadly to the perception of pyrolysis within the wastewater industry. There's been some historic plants that haven't necessarily been successful and have caused concern. So we're fighting those challenges. The calorific value of the advanced AD cake is incredibly low, so our solution to that is blending. Obviously, we've seen plants like the ones in the Aquagreen one in Denmark, where no blending is done, but the calorific value of the input material is much higher than the calorific value that we deal with here in the UK. Obviously, the high moisture content of the advanced AD biosolids means that a high level of drying is required. So we need to make sure that the heat mass balances stack up, which is again part of the problem. The regulatory landscape in the UK is quite uncertain at the moment. I know in the EU there are current challenges to the directive, which excludes biosolids, biochars from the agricultural fertilizer directive. We don't have that challenge at the moment in the UK. but the regulation is very much in motion, and we don't know which side at the moment the regulator is going to come down to. We're actively supporting development groups in terms of kind of lobbying and putting our case forward, but we'll see how that comes out. And the concentration of heavy metals is also challenging, and this is really varied from biosolid to biosolid because of the nature of the way the biosolids are transported around the water network, and some of them can have particularly high contaminations of metals like copper and nickel. So we have to do potentially extra pre-treatment work on areas of old pipes, in effect. I'm conscious of time, so our next steps really are to complete our program of works in terms of our blending. We're working on a series of end-use cases for our biochars. We are working with low carbon and zero carbon road surfacing organisations. We're working with plastering and render organisations for the building trade, and we're also working on some development of some geopolymer cements with our biochars, as well as obviously considering the agricultural fertiliser route as well. So that's the project in a nutshell, and yeah, we'll move on to the questions then, Christian, if that makes sense.
Yes, thank you very much.